In today's session, we're going to talk about Python, and we're going to look at how we can actually implement the Python programming language in our Grasshopper models. And that's going to allow us to do some really cool things with our Grasshopper models that we couldn't otherwise do with Grasshopper alone. And we're going to spend the next two sessions actually diving into Python. We're going to do a basic introduction today, followed by a demo of implementing some basic scripts using Python and Grasshopper. And then next week, we're going to have a more advanced version where we're going to look at how to actually implement custom functions and classes in those Python scripts. And after these 2 weeks of Python, then we're going to get into our advanced modeling tutorials, where we're actually going to use some of these techniques, both in Grasshopper and writing some Python code to implement more advanced workflows in our generative models. So before we get into the details of Python, if you've never used a programming language before, or maybe you're just getting started in Grasshopper but haven't used like a text-based programming language, it's worth spending a little bit of time talking about what exactly is computer programming and where does the programming language live in our kind of current understanding of software and how it's developed. And basically, when you use a piece of software in your computer, we split this kind of package between the hardware, which is actually the computer, the processor that's running the software, and the software itself that's actually like doing the tasks that it's supposed to. But if we look a level deeper, in the software itself, there's actually two components there. So every software is like this. You have the user interface, or what we call the front end. And the front end is basically the display of the software. It's that part that captures all the user interactions. It's the thing that you actually work with when you use a piece of software. But behind the scenes, behind that graphical user interface is the actual code that's running the software. It's the actual computer language, the computer code that's executing all the commands based on how you interact with that software. And that code that runs the software is written in a programming language. So let's start by going over a few common terms just to sort of get over any misconceptions about what these things are, because you hear a lot of these things like algorithms and scripting and programming sort of used loosely and interchangeably out there in the computational design community. So let's just go over what these things are and how they're different. So when you hear about an algorithm, or you talk about algorithmic design, an algorithm is actually a really loose term. Algorithm, all it means is an algorithm is just a set of instructions. And when applied to computer programming, an algorithm is a set of instructions written for the computer that the computer needs to execute. And at the end of the day, even though our computers are very powerful nowadays, computers are very simple machines. All they can do is just execute commands one by one, and the algorithms are the way that we actually create those commands to run on the computer. Now, a computer program, like a piece of software, is just a set of algorithms that work together. They're interrelated, and they work together to achieve a specific purpose. So a word processing software is a computer program which combines a bunch of different algorithms for accomplishing what a word processing software needs to do. So there will be an algorithm for loading a file, for saving a file, for inputting text, and all those different algorithms work together to achieve what the software needs to do. Programming, computer programming, is the process of writing those computer programs. And a programming language is basically the system for representing those computer programs. So programming language is like a toolkit for you to express your commands, all those algorithms and instructions, to a computer. And this system, it could be visual, like we see with Grasshopper, or more often than not, it's text-based. And we talk about computer programming languages, in a way, they're similar to human languages. For us, we use language to communicate from one to the other. So I use a language to communicate to you, information that I want you to know. And it's the same exact thing for computer programming languages, But because computers are very different from us, computer languages are somewhat different from human languages. So with a text-based language, you still have words that have meaning, but usually the syntax and the grammar of how those words come together is very strict, because when you talk to a computer, you can't leave anything up to interpretation. Computers, again, are very simple, so you have to tell them exactly what you want them to do, and there shouldn't be any kind of interpretation or leniency there. And just like human language, there's a ton of different programming languages out there, and some of them are similar or different, but they're all serving the function of communicating something to a computer. Now, when we talk about scripting, you hear this word a lot in computational design. In design, we don't often talk about programming or like writing programs, because we're usually not putting together like fully fledged software like word processors or things like this. So when we talk about scripting is like writing computer programs, but not a full software, more like just a simple algorithm just to accomplish a specific thing. And these scripts, as we call them, are usually like chunks of code that aren't very big, and they're meant to just run once to accomplish a specific task. So whereas you might have a computer software program that's like a whole operating system that does tons of different things, a script might be just an operation to like take a building and split it up into a number of panels. So you have these kind of single purpose operations. So let's look at, in terms of our design tools, comparing visual programming, which we already have seen with Grasshopper, to this idea of scripting. And really, these are just two different programming languages, or two different ways to express operations or algorithms to the computer. And when we talk about design and design software like Grasshopper, these algorithms are usually telling the computer things that we want it to do in terms of geometry, right? So these are just kind of interfaces for defining what we want the computer to do to create our geometries for us. And really, they're very similar in many ways, but they're also can be quite different. So you see here on the left image of Grasshopper. So Grasshopper is a visual programming language. It's still a programming language, but here we don't write text. We don't write our instructions as like text code. We actually represent our instructions by linking together multiple components that all represent small operations. So if we want to create a complex geometric process, we first break it down into its constituent parts and then piece those parts together to create the entire definition of what we want the computer to do. And we represent those things as visual elements. And visual programming, Grasshopper has become very popular, and it's probably one of the most popular examples of visual programming. But the idea of it didn't start with Grasshopper, but it is relatively new when you look at the entire evolution of computer programming. And that's just because computer screens, visual interfaces, are also relatively new. When computers came out in the 50s, you didn't have these graphical interfaces. You would actually have computers that would like type out text as an output, or you had other ways of interacting with it. And this kind of like graphical user interface is actually a relatively new development. So you see that text-based programming is kind of the origins of programming, and these kind of visual programming languages have evolved, more in recent years. But you've seen how popular Grasshopper has become. A lot of that is due to the fact that these visual programming languages are just easier and more intuitive to understand, especially for designers who are used to working with visual elements in the computer, as opposed to like writing commands in some arcane kind of programming syntax. Nevertheless, programming languages have existed in design tools since before even Grasshopper or visual programming, in the form of scripting languages. And here you see on the left an example of like a text-based programming language. You see, we have text written, but it follows a specific syntax. You see things highlighted, different ways of expressing things mean different things. And you see a fairly kind of strict formatting to that text. So when we get into the comparing, visual programming versus scripting or text-based programming, we can also think about it as being two different ways of programming our logic for our algorithms. And visual programming, like Grasshopper, is a functional approach to programming. And what we mean by functional is that we're expressing our operations, we're expressing what we want the computer to do as a sequence of interrelated functions. So each function serves a purpose, and when we hook them together, they basically communicate between their inputs and outputs and create bigger functions, right? But in this case, we're not telling the computer explicitly like what it should be doing at each step of the way. We're just saying, apply this function to this data, and then based on the output, apply this other function. So we're creating this kind of path for data to follow through all these functions. And so Grasshopper is a functional type of programming language. There are also text-based functional programming languages as well. But when we get into text-based programming, usually this is more of a what's called an imperative approach to programming, or imperative programming. And as the name implies, imperative means you're telling the computer exactly what you want it to do. You're not just giving it a function and some data to pass through that function. You're telling it step by step, line by line, exactly what we want it to do at each point of the process. And so we have this idea of a script as a series of lines of code forming an algorithm. And each line is read sequentially by the computer and executed sequentially by the computer. So this actually creates a different way of programming a computer. And this is really where the core is of why I use Python a lot in my computational design, and why I also teach it as a kind of extension to Grasshopper. Because what you'll see is when you start with Grasshopper, it's very intuitive, it's very easy. You create a bunch of points, you pass those points in a circle, now you have a bunch of circles. It's very intuitive. But as you get more complex and you want to start doing more complex operations where you're making decisions along the way to do things based on certain inputs, using a purely functional approach in Grasshopper becomes very challenging. And you have this kind of curve where Grasshopper is very easy to learn and pick up for doing very simple things. But you get to a point where the more complex stuff you're doing, it becomes actually very difficult and cumbersome in Grasshopper. And you have all these kind of workarounds for making it work in Grasshopper, something that would actually be much easier expressed in an imperative way using text-based programming. And at some point, you actually get into things, and we'll look at them in class, in this class even, things that are actually impossible to do in Grasshopper, like writing recursive functions. You just can't do it in a visual programming language, but you can do it in Python. But what's great is nowadays, we don't have to choose whether to use Grasshopper or Python. We can actually embed Python directly within Grasshopper code and actually use whichever one is most appropriate for what we're trying to do. And I'll get into more of that in a little bit. But when we look at programming languages, there's a ton of them out there. And programming languages have evolved with computers for the last 70 years. And you have some languages that are older, you have some languages that are newer, and some languages are meant for different kinds of applications. And there's really like too many of them even to list, but there's a few that are very popular that you might have already heard of. So over here on the right, you have like the kind of web languages, and these are really meant for what we call front-end development. These are languages that create algorithms that run in the actual browser, in your internet browser, and they are based really on interaction. So languages like JavaScript, PHP is a little bit more old school, but they're really meant to like be dynamic languages, and they really curate the user interaction of how the user interacts with the website, and what happens when they click on a button and this kind of stuff. So these are kind of like dynamic languages. You have the more kind of like old school languages like C++ and C#. These are part of the Windows.NET framework. And these are really languages that are very kind of, they prioritize speed and robustness, and they're really the languages that people use to write entire software programs. So if you have a software program on your computer, like Microsoft Word, or even like the Windows operating system itself, it's built on the backbone of these like mega kind of heavy-hitting computer languages. And, typically in computer languages, you have this trade-off between something that's very easy to use and easy to learn, and something that runs very quickly. And that's a kind of trade-off. So C++, for example, is very efficient. It runs very quickly. You'd never develop a software, that of any kind of scale in anything but C++, but it takes a lot of work to learn it and a lot of work to implement. And there's a lot of rules for how you use it to make it that efficient. On the other hand, here we have Python, we have Java. Java, used to be very popular. It's gone a little bit out of fashion lately, and Python's really taken over. And these are kind of like scripting backend languages. So a lot of times these are languages that are used to write the server-side code for web applications, but also they become very popular for, just writing code in applications where you're not really developing computer software. In the old days, the only one type of person wrote computer code, and that was a computer programmer working on computer software. But nowadays, programming is really becoming a tool that's used by every industry and not just computer software development. So you have people in finance writing scripts to automate their workflows. You have people in science and research writing scripts to process data. And you have architects now writing code to automate their workflows and accomplish things they couldn't do. So these more modern languages, and especially Python, which is one of the most modern languages we have, really have prioritized ease of learning and ease of use and ease of implementation over being super efficient. And these are the kind of languages that are more often you look at when, if you're a designer trying to use programming and not a programmer trying to build a piece of software. And in this class, we definitely will look at just one of these, just Python. And like I said before, the cool thing now is that you don't have to choose, do I use Grasshopper or do I have to learn computer code? With Grasshopper, you can now embed computer code in Python directly within your Grasshopper definitions. So what we'll see in the demo is we have one component in our Grasshopper canvas, which is the Python component. And when you double click on that Python component, you actually get a full code editor embedded directly within Grasshopper, where you can write some code here and it'll run in Python, and you can actually create inputs and outputs that connect that code directly to your Grasshopper definition. So what you can do is you can create these kind of hybrid definitions and use Grasshopper code components where you want, where it's easier, and use Python code where you need to for doing things that you can't do with Grasshopper. And this kind of hybrid workflow is something that I've been doing for years, and I really recommend it, and I love teaching it because, Python will really unlock a lot of potentials in your models. And the reason why I teach it even in this foundational class is from the very beginning, a lot of our models that we develop, our generative models, will do things really cool things that just are very difficult to do with Grasshopper, but fairly easy to implement in Python. So it will unlock a lot of capabilities for you, but you also don't need to follow this huge learning curve. You don't need to say, okay, I just learned Grasshopper and now I have to learn this whole new computer programming language. You can just do a little bit. You can put in this component into your canvas and just write a couple lines of Python code, just to do something very specific, and build on it. And once you get there, you can make it more complex and sort of learn as you go through practice, rather than sitting down with a book and learning the entire Python programming language. So my goal is just in these 2 weeks, we're going to learn enough Python to get started building Python into our models. And then as we go throughout the course, as we get into more complex models, we're going to keep seeing Python code. We're going to keep reiterating, learning new functions, learning new methods as we go. So let's take a quick look at comparing an algorithm for doing something with our geometry and how that looks like in Grasshopper versus how it looks like in Python. Here we have a really simple example of a cylinder, and we're defining that cylinder now. Instead of just making the cylinder in Rhino, we're going to define the process for making that cylinder based on a couple of operations. And throughout that process, we're going to expose some parameters that will control what our cylinder will look like. And so you see here in Grasshopper, when we develop this algorithmic flow, we have to break down what we want into components and then kind of piece together the set of operations to get what we want. So in this case, our process is for making a cylinder is basically we start with a point, and then based on that point, we're going to create a circle, and then we're going to extrude that circle to create the actual cylinder. So it's basically 3 steps in our process. And here's what that looks like in Grasshopper. we start with creating a point at the origin. We pass that point to the circle component, which will create a circle using that point as the center. And then here we have an input for the radius, and we set that radius with a slider. And once we have that circle, we can pass it as the base curve to the extrusion component. And the extrusion component has another input for direction, where we pass the vector, the direction that we want that extrusion to go. And here we use the Z direction. And then we'll pass in an input to actually set the scale or the amplitude of that vector, which is the amount that the extrusion, that the curve will actually extrude. And then so finally, our cylinder is contained within this extrusion component. You can see here, this is what we mean by a functional approach, right? We define the cylinder as a set of functions that take in data like a point and two numbers, and by flowing through those functions, get where we need to go. But importantly, we're not telling Grasshopper exactly what it needs to do at each point. We're not saying first do the point, then do the circle. We're just stringing this all together, and then Grasshopper has a way to basically start at the end and calculate all of its dependencies to get to where it needs to go. But we don't actually tell it, should you run the circle command first, or should you figure out the vector? These are kind of in parallel, and Grasshopper can figure out what it needs to do when to accomplish the end goal of our script or definition. Now let's look at the same exact example in Python. Okay, so in Python, we have this window here. You can see I have the Python component on my canvas, and I'm not putting in any inputs. So this script doesn't depend on anything being input into it. But here I have one output for the cylinder, and this is going to generate the exact same form in Rhino. And let's take a look at the code. So we start with an import. We import the Rhino geometry library so we can actually work with Rhino geometry. And then it's really the same set of operations. We have like 5 or 6 components here. We have 5 lines of code here. The first line of code creates a point from the Rhino library based on a set of inputs, 0, 0, 0, just like we have here. And that creates a point, and we store it into this PT, which is a variable. So a variable is like a container that's now storing that point information, just like we have this component being a container that stores that point, right? It's the same kind of thing. And now we declare another variable called radius, and we set that to be equal to 5. And this is just like creating a slider with the number 5 in it. And now the next line of code, we actually create that circle by running the circle method from the Rhino geometry library. So this creates a circle, just like this component does, right? We give it a center point. This is our PT, the variable that's storing our point, and we give it a radius. So we pass these 2 inputs into this function. It creates a circle. And then here we convert it to a NURBS curve. And this is where Python gets a little bit trickier, because sometimes you actually have to convert geometry types, like from a circle type to a NURBS curve type, to make some of these functions work. And we'll get into more of that in detail in the demo. But this set of functions creates a circle that we store in a new variable. Now we declare another variable called height, which is the same thing we do here. And that's going to be 10 units. And finally, we have a third function from the Rhino library called extrusion. And we basically create that extrusion, and we pass into a set of inputs that represent the base curve. So that's our circle, the height. And then here we have a flag for should you have a cap. And this is also a little bit different than Grasshopper. In Grasshopper, extrusions are always open, and you have a separate component to cap them. In Rhino, or in Python with the Rhino library, extrusions have this optional flag of cap. And if you set it to true, it'll actually cap that surface. So a few things I want to point out here. You can see that a lot of things are the same, right? And if you've learned Grasshopper, learning a programming language is something new, but in terms of how you think through problems, it's still really the same process. So if you've learned how to think through a problem computationally in Grasshopper and piece together a solution as a component of parts, it's not going to change much when you get into Python. The big thing that will change is, number one, the syntax of Python itself, which is how do you write these things in Python and how do you structure your code? And the other one is actually when you're working with Rhino geometry, learning how to work with the objects and methods within this Rhino geometry library. Now, I'll get to this later in the slides, but this Rhino geometry library is exactly the same geometry operations that you are using in Rhino and you're using in Grasshopper. But in Grasshopper, they tend to be wrapped in a more kind of user-friendly way, where when you use them in Python, you're using like the core Rhino library, which sometimes can be a little bit more complex. But we'll look at a lot of examples, and so you can get a kind of intuition for how these methods work. And by the end, if you get a lot of practice, you're going to be thinking in these two ways all at once. When I work nowadays and I start making a model, I start in Grasshopper always because it's easier. I know the Grasshopper components. I can put things together quickly. And then when I get to a certain level of difficulty, I'll switch to Python. I'll start coding. And I also know a little bit about what all the different components and objects and methods are within this library. But you're going to have to kind of understand both to work in this hybrid way. Okay, and it's just as I mentioned, one of the big advantages of working in Python within Grasshopper is you actually get access to this Rhino library. And at first, this is going to seem confusing, like working with this library is a little bit more difficult than just pulling components from the ribbon in Grasshopper. But you'll see over time that this is like a really powerful thing, and it's a huge advantage because when we're in Grasshopper, all we have access to is the components, which are using the geometry library code base, but they're telling you what you can do, right? So you can only make a circle this way or this way. When we pull in this Rhino geometry library, we're actually pulling from the exact code base of Rhino, and that's called Rhino Common. So Rhino Common is a standard API, application programming interface, which was written by McNeil, who made Rhino, as basically the foundation on top of which all McNeil's apps are built, right? So instead of thinking about Rhino as like a program which embodies all of those geometric operations within it, what McNeil did was they took all the geometric stuff out and they made this kind of code base, this foundational API, and then they built Rhino on top of that. So Rhino uses this code base, and Grasshopper also uses the same code base. And now if you're in Rhino for Windows or Rhino for Mac, or now we have Rhino Inside or Rhino Compute, all these different places where Rhino is living uses the exact same API, and it's this Rhino Common. And you can see down here, this is where you can get the documentation for everything Rhino Common does. Now, what's really cool about Rhino Common and using it from within Python is it gives you access to all of the geometry. Yes, so rhino.geometry has all the geometric types like points, lines, circles, curves, surfaces, meshes, everything, and all the methods that work with those types. So if you want to intersect two lines, there's a method for that, etc. But you can see here, geometry is just one component of this library. We also have all these other components. And if you take a look here, we have display, we have file IO, right? We have render. This is actually all the nuts and bolts of what Rhino makes Rhino work. So what I want to tell you is if you take the time to learn Python and get through the learning curve of learning how to use the Rhino library in Python, you're going to be able to do so much more than just making geometry. In Python code in Grasshopper, you can control opening and saving a file. You can control how geometry is displayed, colors, everything. Everything is available to you, and it's really, really cool. It is complicated. It requires a lot more learning than just using Grasshopper, but if you just learn a little bit, the world will kind of open up for you. Okay, so that's the presentation for today. Let's get into our demos. So in the demo today, I want to show you just a start of what we can do with Python in Grasshopper. And we're going to develop a really simple script from scratch. And we're going to end up with this script that basically creates this very simple tractor point process where we create a grid of points, we'll create a circle each point, and we'll derive the radius of that circle from its distance to a certain other point in our Rhino file.